Welcome, everybody. This is the second podcast of Twisted Transistor, and today we have a special guest, Darren Myers from Parasound. And today we're talking about phono preamplifiers. Darren, the floor is yours.
Thank you, Mikhail. I'm happy to be here and walk you guys through various different aspects to designing a phono stage. I'm going to walk through different ways of implementing the EQ, the RIAA EQ, and also just how you would do calculations for gain and where we place gain, how the loading affects cartridges. We'll talk about that. We will talk about the accuracy of the curve. We'll talk about how to pick operational amplifiers and what the advantages of certain opamps are, and then we can touch a little bit also into talking about integrated monolithic designs versus discrete designs as well. So there's a lot to discuss here, but I'm excited.
Yeah, I'm excited too. It wasn't easy getting such an expert as yourself, but I'm happy that we can finally do it. And you are an avid vinyl lover. Is that true?
I do. I love vinyl. I think I have a pretty balanced approach to the way I approach the source gear. I mean, we need to what I think is the most important aspect is to have the best version and the best copy of whatever recording you're trying to reproduce, right? So
yeah,
in a lot of cases, in the modern day, the best copy that you're going to be able to have is the high res file, and I would argue that the best source would be, either, probably on a really nice server, and the file locally on a SSD would be one of the best sources that you could have. And, if that recording was native in digital, it's going to be hard to, I think there are some exceptions, but it's going to be hard to beat the transparency of something that is native and modern. But as we go back in time, if we look at 1950s and 60s jazz, for instance, a lot of the digital recordings that were when they were transferred from the analog tapes in the 1980s were done in a very the process was very early and rudimentary at the time, and it really does not sound very good. The tapes were fairly old by the 1980s and the 1990s when they did a lot of those transfers. So still, even though vinyl from an objective perspective is not a strong format, there are many examples of the best sounding copy of a recording is on the vinyl format. And it sounds a lot better than the transfer to digital that was there. So vinyl will always have a really strong use case in our systems, because there are there's a whole slew, there's millions and millions and millions of recordings that are really lost when it comes down to their fidelity for digital transfers.
Yeah, it's true. It's true. And you mentioned the ultimate fidelity of being as close to the source as possible, but what about the celebration of just using vinyl? Is that something that gets you also?
I do. The process is amazing, and the romance that comes along with having that tangible element is something that I cherish. Other times I'm not in the mood. Other times I just want to stream something. But there's nothing like cooking and putting on a record and seeing I have my turntables actually access or they're near my kitchen, so I can be cooking and I see the the turntable playing, and so there's something that is really romantic about the process, and also the fact that how does this work? How or it's such a miracle that that it sounds as good as it does. I do think that when you think about the process of dragging something through a groove of plastic that was stamped, it's quite incredible that it performs the way it does.
Yeah, I agree with that. Even if you consider like vinyl having like this 50, 60 decibels of dynamic range, it's still 50, 60 decibels. It's a lot.
It's a lot. Oh yeah, I think I see a lot of arguments on the internet saying, well, if it's only 50 or 60, it has to suck. Like there's nothing to get out of it. Well, your recordings, a recording that has 20 is a lot.
Yeah.
So it exceeds what the recordings have on it. And then if you look at the dynamic range database, if you go up there and you sort on the highest dynamic range record or recordings, most of the vinyl format at the very top. And we'll talk about a little bit about maybe why that is. But a lot of recordings, old analog recordings actually have less compression. And so they have a wider dynamic range, or some of them do. I'm sure you can find some pretty bad recordings on vinyl. Okay, let's dip into this because there's a lot to talk about. So this is LT Spice for those that are not familiar with LT Spice. And what we've done here is set up some test parameters for what we're going to be doing today. So on the left side of my cursor here is only for test. It's not something that you would build into your phono preamp. This right here is the input to the phono preamp.
Okay.
But what we've done is we've created an inverse RIAA so that we can create what you would see coming off the test record if it was playing, a flat signal from, in this case, 10 hertz to 20 kilohertz. So if we had a flat signal, something that at the output of a phono stage would be 0 dB across this bandwidth, then this is the signal that you would see coming out of the cartridge. And I've added an amplifier here that is to buffer the output of our inverse RIAA and the input of the phono preamp. Yeah, actually, in this case, you don't need this buffer, but I always do put that in there just so that I don't have a situation where it does interact with the input of something. Yeah. And then I've spent 3 hours trying to figure out why something doesn't make sense, and it's really because I didn't isolate it. So I always isolate my impedances in LT Spice and sim programs, just so that I don't make that mistake. But that's why that's there. So this is just trying to give us an accurate test signal, so that then we can test, the performance of our phono stage. So if we look at the signal coming out of the cartridge, we see that the lower frequencies are massively attenuated and the upper frequencies are elevated. And the span of this curve is roughly 40 dB from the top to the bottom. And you can kind of see that at the top, we have negative 20 dB. Bottom, we have roughly negative 60 dB, span of 40 dB. And in this curve, this was something that was spec'd by the RIAA, and this is it comprised of 3 time constants to create this profile. Okay, so the reason why this was done is because if you were to have a flat signal where there's no attenuation and no EQ cut on the record, the lower energy would literally cause the tone arm to jump out of the groove. So what they've had to do is apply a correction to it so that at low frequency the amplitudes are really small, and at high frequency it's much higher. And so this way we can then apply the correction to this and then have the flat signal. So it's just the inverse transfer function applied, and then you're back at where you were, which is hopefully flat frequency response if the phono stage is designed correctly. But all of this was done to optimize the vinyl format. Without this, without this, you wouldn't have very good performance. You would have maybe the high THD at low frequency, or you would be dealing with the skipping and jumping grooves when there would be a lot of bass in the recording. So this is something that is necessary and was something that engineers spec'd, and there are different curves like the Deca curve, but the RIAA curve was the one that was adopted widespread, and that's a whole nother world. People argue about what's Deca and what's RIAA, and some people say that everything was RIAA. I don't know too much about that. Michael Fremer could go on about it, but I don't know much about it. But so the RIAA curve was the one that was adopted, and it's absolutely necessary. So this is what's happening. So what we have to do is we have to apply the inverse transfer function. We have to apply gain to this entire waveform because it's very low amplitude as well. So it's coming off the cartridge here at let's say at 1 kilohertz is going to be roughly 5 millivolts for an mm here. Okay, so we have to apply, in order to get to a line level output, we want to apply I was talking about the inverse RIAA and it being very necessary on a vinyl record. So that's why it's very necessary to have this inverse that's why it's important to have this EQ curve built into the vinyl format. So this is what we're seeing outside of the on the output of the cartridge. And in order to get the this is going to be roughly 5 millivolts coming out of let's say a moving magnet, an average moving magnet. And what we need to do is we need to also boost this signal up to line level. So not only correcting the frequency response, but we need to apply a lot of gain to that 5 millivolts in order to get the line level on this side. And so what's common with a moving magnet phono stage is you're looking at anywhere from 36 to 40 dB of gain at 1 kilohertz. So that's the way that these things are spec'd, is usually at 1 kilohertz, just because it's a reference, and there's going to be a lot more gain at low frequency because we have to bring this all the way up. And then we're going to, also apply gain at high frequency, but it's going to be less than at 1 kilohertz.
Yeah, which is kind of, it's fine because usually most of amplifiers will have lower distortion in the low frequency range. So actually it's not that bad.
Yes, exactly. So there are some things that work into, having less open loop gain available in amplifiers. And so if you have to, have less gain at high frequency, it does help you apply more feedback at high frequency.
Yeah.
We will talk about that shortly. We'll come back to that when we're talking about the amplifiers, but
all right.
That's roughly what you're looking at here is up to a gain of 100, which is 40 dB at 1 kilohertz. And this is the way I've configured this phono stage, is to have around that gain at 1 kilohertz. So looking at the input here, we need to work on our first stage. And so our first stage, you'll notice that we have our loading components. And for anybody who's familiar with, MM phono stages, it's very common for them to be loaded at roughly 47K and 100 puff. Maybe sometimes that's 120 puff. It's important to remember that the cable capacitance is also factored into this right here. So one thing that's really cool about using Spice is that we can simulate, for instance, we could simulate a cartridge. So a cartridge has an inductance and it has an impedance. And in this case, it's just going to be purely a resistance. So we can say that this cartridge is going to be roughly, 1.5 kilo ohms, and its inductance. So its DCR is like, say, 1.5 kilo ohms, and its inductance is going to be, let's say, something like 650 millihenries. And if we then, I'm going to use this is a bit more advanced, but I'm going to use the step param feature, which is going to actually be able to step out various different loading resistors. And we can do this with our capacitor too. But it's going to run simulations on anything we put in this list. And you can make this list as long as you want. And you could go to ChatGPT, for instance, and get it to run a script on, any sort of algorithm to create a huge spread or a huge list that you want to test if you want to test, for instance, hundreds of values at a time. So it's a really powerful feature in LT Spice. So we're gonna go ahead and we're gonna simulate this now, and I'm gonna put this on the output, and I'm doing this because I want to show the differences in the loading resistors on a moving magnet phono stage, what it does. So it's affecting the damping. So we have an underdamped response here, and we have a lower Q response, and then a Q that's obviously less than 1 on the blue line. So this is going to affect, look, this is 10 kilohertz right here. So that's why you hear such a big difference when you're changing these values on the loading on the input. This is really what it's affecting. And if we were to change the capacitor, we would see very similar behavior. So it's the combination of the two that is affecting the damping response from the cartridge. And that's why we have these here. If we didn't have this, like for instance, if we go to view and we go to legend, this is showing us which line's which, right?
Yeah.
So, that this Scion or whatever they call it, this is the 220. That's the 220K. So if you just didn't terminate this thing, or if you terminated at 1 mega ohm, you'd get a huge peak with a massive Q. And so, this is a very important resistor. Very important to load your cartridge correctly, and also to have a correct capacitance on the input that also factors in your cable capacitance. And the cable running to your moving magnet is going to be very important. And that's why it's nice to know the capacitance per foot of that cable that you use, so that you can calculate it into the overall loading that you're gonna have.
So if we would have like some sort of a short takeaway from this part, how would you say was the best way to tune the input circuit? So start with capacitors, because we have the cable which we won't be changing, and try to get the capacitors in the ballpark of what the cartridge expects to see, and then tweak the resistance.
So the manufacturer usually specs a certain resistance that they want you to load it at. So I would start with the manufacturer's recommended value for this resistor. So 47K, for, let's just say that we're talking Ortofon, 2M red or 2M blue, like very standard MM cartridge. 47K. So let's start with 47K. And what I would do is actually step the capacitor, right? So we could let's find the right capacitance to load the cartridge at. So now we can just apply the same thing. So we put in our variable in the capacitor, go over to our list. We change this for capacitor values. Let's start now at 100 puff, go up to 120, and then we'll do one at 220, and let's look at what that brings.
Yeah, it's important to know to use real values which you can get capacitors in, which is usually the E96, E48, and so forth.
Yep, exactly. So here we go. So I'm going to bring up our legend again so that we know which one's which. Okay, so we can see that in this case, 120 seems very, very nice. That's probably closer. What we want is something that's close to, 0.707 in the Q, and have a nice damped roll off here. 220 would start to peak it, so this could start making it sound brighter, harder transients. So we want to, 100 to 120, but what I would do is go with 100 here, because we're going to have a cable, right? So we have to add that cable capacitance, and so that's why a lot of times you see 100 being spec'd on the input, because they're making some room for 20 to 50 puff of cable.
Yeah, there's a reason those are the jelly bean values.
Yep. Okay, so now that we've discussed that, so I think we understand why we need those components. Let's go over to our first amplification stage. What we want to do is apply some gain to the entire signal. So if we look at, well, now I have to run this. So if we look at the output of this relative to the input of this stage, you can see that what we've done is we've applied widespread or wide bandwidth gain to the signal, but we haven't corrected any frequency element. And one would ask, why wouldn't we correct the frequency element in this stage? And why are we not applying more gain in this stage? So the answer to those two questions is that in order to start applying the correction, we're going to need to introduce some impedances in order to use attainable values and practical values of capacitors, right? So if we were to move this value down a factor of 100, that means that capacitor would have to go up a factor of 100 to have the same time constant in this section. So the reason why we wouldn't be able to use a higher impedance in these corrections is noise. Noise is something that's very important in phono stages because you're going to have so much gain. In this case, from the input to output, it's going to be a factor of about 100. So whatever noise you have on the input, the output is going to have 100 times more noise. And so the actual resistance creates noise by definition. And so we want to make sure that we get the signal up at a higher level where now this resistance isn't, the noise of this resistance isn't dominant anymore. So that's the first reason. Now, to answer the second question of why not apply more gain than just this, we're applying 23 dB right now in this stage. The reason why you don't want to apply too much gain is because you are going to clip and run into headroom issues right here because you have such a difference in amplitude from the low frequencies to the top, which is 40 dB of difference. You're going to actually clip the high frequencies because we're so boosted that I can't apply, if I were to apply 40 dB in this stage, it's going to cause an issue where the high frequencies clip before the low frequencies. And that is not desirable. So it would cause an issue with the overload specification of the phono stage, which we will discuss after we circle back here.
Yeah.
So that's why we're only applying so much. So it's this middle ground where we're getting the best of signal and noise side of stuff, and we're also getting the best of the overload, which is really a compromise in the end.
Yeah.
You know, we were to boost this stage massively, then we would not have a great overload spec, but we would have a situation where this impedance right here wouldn't be dominant at all. The noise coming from this resistor. So that's why we have to be careful how we distribute gain across the phono stage. So traditionally what we're going to be talking about right now is a hybrid RIAA. It's my top choice for a DIY phono stage. I think it offers the best compromise in the way that we're going to do RIAA. So what that means, hybrid RIAA, means that we are splitting the time constants up now, and we're going to be having a passive time constant for our high frequency, which is going to take place at 22 hertz. And then we're going to be splitting up the other two time constants are going to be split up in an active filter in the feedback of our last stage, one at 500 hertz and the other one at 50 hertz. Okay, so those are the three time constants that make up the RIAA. That was something that is spec'd by RIAA as far as the definition of the curve itself. So so now what we need to do is we need to apply overall 40 dB at 1 kilohertz. So far we've applied 23 dB, which means that we have 17 dB left to apply in the second stage. So moving on to we discussed the passive element here, the passive time constant, and then moving on to the last stage, we are.
Excuse me. If we can go back to the first stage, because I know that will confuse some people.
Yes.
C1 is only to create low pass filter for RF rejection. Yep.
Yeah. It's so C1 is that's a great question. And C1 is what's called a lag capacitor. It is meant for multiple things. One is that, yes, we are creating a pole in far up that is going to limit the bandwidth of this stage, and it's going to create a low pass filter.
Yeah.
It is, in this case, going to be used for making sure that we don't have RF pass through this stage and cause slew rate induced distortion of our of not only this amplifier but the amplifiers that follow.
Yep.
And so, because if you were to have a signal in the many of megahertz, you could easily run into a situation where a amplifier starts to go into slew rate limiting, where it becomes very nonlinear, and in that state, it's going to actually demodulate that RF at high frequency and roll the low frequency components on that signal down into the audio band. So you can actually hear RF when it's getting hit with electronics that go into that are being slew rate limited. Maybe people listening have run into a situation where tube amplifiers have picked up radio stations, or phono stages have picked up RF noise or radio stations, and this is the reason why not only they would do that, but the reason why we would have C1. We also care about the stability of the amplifier and the transient response, which are intertwined, as far as if it is in an unstable state, that you're not going to have very good transient response. You could have peaking, overshoot on the transient. So we want to make sure that we have a lag capacitor so that we can make sure that the amplifier is not going to misbehave in any way. So there are multiple reasons, but probably this stage would operate just fine from a stability perspective if we used like a 2134. It's just that we would want to filter RF, like you said. Yeah. So that's exactly the number one reason for that capacitor. So moving on to our second stage, this is where we have to apply the EQ. We have to apply the inverse transfer function to get back to a flat frequency response. And the top of the going back here, we see that we've applied a 40 dB spread between the top and the bottom. So remember when we were talking about overload and how we can clip the very top of this area easily because of how much we need to boost in the low frequency. And so, or I should say, because how attenuated the low frequency is. And so what would be advantageous is to roll off the high frequency passively before we apply gain. And let's just look at what happens right after this passive network here. So if we look at, we need to go here. So this is before it, and then this would be right after. Okay, so we've rolled off the top, and now we've applied just the top time constant, which is at 75 microseconds. And now what we've done is we've changed the spread to be 20 dB instead of 40 dB. And that's really advantageous because now we can raise the whole thing up without worrying about clipping this.
Yeah.
So that is why I recommend the hybrid. Well, that is one of the reasons why I recommend the hybrid RIAA, is because it has this advantage of headroom over, say, a standard passive one.
Mm-hmm.
There are also some reasons why, for instance, you brought up having to have, say, enough open loop gain or feedback available in the amplifier at high frequency to apply that gain. And the fact that in a phono stage, because we have less gain at high frequency, that kind of works with some of the disadvantages of amplifiers, just having more open loop gain available at low frequency than at 20 kilohertz in most cases, and how that's advantageous. So this actually helps us even more because this stage, doesn't have to have, it now it has a flatter, the amount of feedback applied to the system from 1 kilohertz to 20 kilohertz is flatter. Yeah. And that is advantageous to not have to change the amount of feedback versus frequency in this sensitive area. I think we can all agree that our ears are very sensitive, right in probably this region here from 500 hertz to 3 kilohertz is an ultra sensitive region for the human ear. And so it's nice not having to have a huge swing in the amount of feedback applied in the amplifier here. So that's another advantage to a little bit more of an advanced concept, but one of the reasons why people have tended to start to go towards these hybrids setups more often. So so now what we have to do, now we have our green line, now we're stuck with this. Now what we have to do is we have to apply our 500 hertz time constant at 318 microseconds, and then we have to apply the time constant at 3,180 microseconds, which is going to be the 50 hertz pole down here. So then we also have to make sure to, at 1 kilohertz, apply 17 dB of gain to be able to get our spec of 40 dB at 1 kilohertz on the output. So we end up with this network that looks like this. I'm going to describe what the components do and how to calculate this, but I want to preface with that there are some pretty in-depth reactions, or there are a lot of variables in this, and changing amplifiers alone may change the curve a little bit due to the parasitics of the amplifier, like its input capacitance, its open loop gain could change these slightly, not dramatically, but it could be enough that matters to you, like, tenths to hundredths of a dB, that could be something that could be affected by the op amp that you use. But and these equations that I have are, they're a good rule of thumb to go by, but there are some more variables if you want to calculate something really in depth, and you can find that on the internet. But to get an idea of how this works, we're going to start off with applying our 500 hertz pole here, it's actually a 0 at 318 microseconds. So what this is we have to take if you wanted to imagine what the time constant, it's this capacitor to this capacitor here. So it's that RC that's really taking an effect. But we have to look at the components around it and how they're interacting with the impedances at certain frequencies. So in order to do that, our equation becomes R23 plus R25 in parallel with R26 times, and that's our R, and then our C value is going to be R24 in parallel with R29. And that, with capacitors, we just add that value. And so that's where you come up with this time constant right here, because the time constant is the resistance times the capacitance. So it's RC.
Yeah.
But we've created a more complex equation just because of how these other components interact with this R value. But this is the C value, and that is the R value for this time constant here. Okay?
Makes sense.
So moving on to our 50 hertz, now we're looking at it being this value right here. So that's the R, that's the C, and so C24 in parallel with C29 times R26 will give us our low frequency pole, which is at 50 hertz. Okay, so that is roughly how that works, and then this value needs to be selected for gain. So the lower this value is, the higher the gain will be, and the higher this value is, the lower the gain will be. These are non-inverting amplifiers. So that means that you have RF, which is this resistance here, divided by R1, which is this resistance here, plus
1.
Yeah. And so that's how that value is created. But as you can see, when you change the gain, you change the pole.
Yeah.
Or I'm pointing to a 0 right now. So, but you change the time constants. So don't you see now these are all interplayed, and this can get really complex very quickly. There are multiple variables that interact with each other.
Yeah.
And so one might say, well, if I'm DIYing an amplifier, what should I do to be able to come up with these values? And now that I've explained what's going on in this circuit, I will say that the good news is that you can come right over here, and we can link this at the bottom of the video, but this calculator will just do all this for you. And so here we go. This is a hybrid configuration, and we can just plug in what we want as far as the amount of gain at 1 kilohertz. And, this is the gain at on the first stage and the second stage. and then we can just get our values that will pop out. Or I'm sorry, you just plug these three in and it'll give you the rest. So
Okay.
if we just say, 33 nanofarads for C1 right here, what do we have? Yeah, 33, right?
Yeah. We do.
Yeah. And then
24.
24. And this is not going to match directly, and I'll tell you why. But so, it gives us our rough value. And you can see it's in the ballpark here, 133 to 132, 2 to 2.2, 14 to 12.4. So it will do this for you and give you the ballpark stuff to start working with. You can then simulate this and see how it works. Again, the amplifiers and the specifications of the open loop gain and the parasitics around the amplifier will change this slightly. And that is one of the reasons why my values differ. This was designed around LM 4562 and also OPA 1662. Okay. I measured this in I've measured this actual design built, and it's very accurate on the AP. So these values are a good a rule of thumb to go by if you're using 1662 or 45 or the 45 on what was 62.
Yeah.
Lots of 62s.
Yep.
So now we've applied that. Now, another thing we have to worry about with phono stages is DC gain. And because you're going to have DC offsets and DC, parasitic DC behavior with these amplifiers. And so on the input here, you're going to have some offset for your amplifier. And that's something when we're trying to find and we're looking for op-amps. For phono stages, op-amps that have a very low input offset spec, generally that's a very good start because we have so much gain, and the gain is going to multiply, that input offset and put it right on the output here. So that can, it doesn't, like, when you think about it really quickly, you're like, well, yeah, but it's just so small, but it adds up so quickly. So at low frequency, we do not have 40 dB of gain. We have 60 dB of gain, right? Because that's at 1 kilohertz, and we're down 20 dB more. And so we have to actually boost that up. And so, even an MM stage has 60, and then moving coil stage has 80. So it really adds up quickly. So we have to be careful when it comes down to the DC gain. And so for DIY stages, I do recommend using capacitors to reduce this the worry of running into DC problems, because once you run into DC problems, it can be a bugger to fix it without some redesign of your circuit. And so the first thing that we can do is we can decouple the feedback at DC. So we can put this, that's what C25 and C26 do, is that if you look at it in the terms of DC, a capacitor is going to be theoretically an open circuit. And what you have is you have a follower at that point, right? Because you don't have any resistance going to ground. And so that just turns into strapping the amplifier like this.
Yeah.
And you get a gain of 1. So that dramatically reduces our DC gain, and it's going to help us not run into massive DC issues, because you could easily, without much care, you could run into having volts of DC here, and we all know that won't be good. That will cause early clipping, and you really want to run these amplifiers where their output is close to 0, so that they have equal headroom on the top and on the bottom.
Why not do it in the first stage?
So one reason why we wouldn't do it in the first stage, and you can if you want to, but the RC value is going to dictate this low frequency roll off. So let's just simulate that really quickly. So I'm just looking at the output here, and I'm gonna lower this value to, let's say, 1 mic. Or actually, I put down there, I've left a note for myself, 4.7 for rumble filter. Okay, let's run that. Let's see what happens to the response. So we're gonna see a roll off. So this is a high pass filter that's being created between the impedance that is seen looking into this, which is also a combination of this impedance and this impedance here. And so the value of this capacitor needs to be large enough to get your low frequency bandwidth to be flat, or your low frequency response being flat here. So, so when we look at it in terms of this value, we've gone from 2K to 100 ohms.
It's a 20 times difference,
20 times different.
Huge capacitor.
Big capacitor, doable, but are you going to be able to find, the quality capacitors at that, at that value? And also, what about money and size? They're going to grow in size. They're going to, maybe you're going to have to settle for, a less superior construction. Like, you're going to have to probably just go electrolytic at that point, where here, you could find a combination of stuff to make things work. If you want to throw some films in there to make it for some bypass values, and then use a really high quality electrolytic, or you could use create like a back-to-back capacitor with polarized, or you could use a non-polarized electrolytic here. But generally, you're going to be able to find, a smaller value or a higher quality capacitor in this value than if we were to multiply it by 20. And so that's the reason why I have that. It's you gotta kill the DC gain somewhere, and it's just more advantageous where you have higher impedances.
Yeah, and also in the first stage, we have the resistors R22 and the R21, but we cannot bump them in value to facilitate a reasonable capacitor, because it will eat our noise performance, right?
That's right. So the dominant resistor for noise is the R21. And that's just because in noise, we're going to be looking at R22 in parallel with R21. R21 dominates in that case. So so we want to keep this low. We don't want to. That's a great point. It's a great point, because we can't move this up to 2K. We don't want to do that because it's going to amplify this noise impedance right here. And so we want to keep it low. And so in order to do that, we want to make sure that R21 is at a reasonable value. And that's what you see on these phono stages is roughly in the first stage, stage, you're looking at 100 ohms for that value, and it doesn't seem to be dominant, or I should say it's not dominant. The amplifier at that point is the dominant noise source, and that's exactly what you want. You don't want to ever have a case where where this noise becomes larger than the noise created on the input of the amp. That just means that your network is going to be too large in value.
Yeah, and why is the R21 dominating? Because you would think that it's the R22 which has a higher thermal noise. So why it's the 21?
In order to see that, what we need to do is we need to imagine that if you were to be able to look into the impedance from this perspective. So you kind of rotate it all around and then look into this node right here. And let's look at the impedance at this point. And what we have is we have low impedance coming down here. It might as well be ground, if we wanted to simulate what these impedances look like. This is ultra low impedance. And so we have R22 in parallel with R21.
Yeah.
And if you look at the lower...
Yeah, the lower value will dominate.
It's going to extremely dominate the overall impedance. So we don't care what the individual values are here. We care about the paralleled value looking into this node. And because of the configuration and the equation that we need to get our gain, R21 will always be a lot lower. So R21 tends to dominate over R22.
I see. So you can tell so it's kind of like the noise that is coming from the R22 is getting shunned by the R21.
Yes, correct.
Okay. Yeah.
Correct. And it's always a summation. You're looking at, the overall combined impedance of this node. So just like where we had to, run this more complicated equation to factor in how the other impedances are interacting with this impedance. It's the same thing with this. Is if we look versus frequency, it is going to be the combination of these two resistors being the definition or what's going to make up the overall impedance that is seen on this node, which is the input of the amplifier. So that is why R21 dominates.
Yeah, and also speaking of the resistors around the opamps, we can't make them too small because we'll overload the opamps output.
Yeah, absolutely. Great point as well. So you might say, well, let's just make this 1 ohm and make this like 130 ohms. You can't do that because so the output of this amplifier is seeing the impedance of now R21 plus R20 or R22 plus R21. So it's seeing a load that looks like this going down. Okay, because it's trying to get to ground. Simply put, we cannot make R22. We do not want to make it 130 ohms because the amplifier, would start to perform very poorly. You would get a lot of crossover distortion in the output stage. It's just not designed, for that. So that's why we pick those values, and it's really this that the amplifier is seeing.
Yeah. Also, I think it's pretty important to say that R27 and R24, they do not load the opamp because they go into high impedance node of the next opamp, right?
So R24 does load U4. It loads it at high frequency. Yeah, so if you see at high frequency, you start getting lower impedance, and so it starts to kick in at high frequency, but at low frequency, it's really high impedance.
Okay. I always found that confusing, so I thought that we should mention it.
Okay, so moving on, we've described our time constants here.
Yeah.
How we came up with them. We described why we need the to decouple the feedback at DC, and then we have a series capacitor here to block any sort of DC that is residual right here. And this is just in a DIY project that you don't want to mess around. You don't want to run into huge roadblocks and large problems. I would highly suggest just going with some sort of bypass or a coupling capacitor right here. It just makes your life a lot easier, and you can buy a really nice one. You know, you could buy a Mundorf or a MyFlex or whatever you want to do here. But this one, you will want to make sure it's an audio grade capacitor of some sorts, meaning, even a film capacitor off of DigiKey or Mauser. You don't want it being, a polarized electrolytic. You really would like this to be a nice quality film. So, I don't want to spend too much time on this because we have a lot to talk about, but the alternative to these DC methods that like R26 and R25 and R27 would be to run what's called a DC servo and actually feed DC back into the usually the virtual ground, which is right here, to correct the DC and be able to directly couple. And I don't want to get too far into that. That is a more advanced technique. There's probably plenty of people watching who are familiar with doing that, and you're free to add a DC servo with this design, and it will work. But for somebody who wants to build this, and it's you're starting out and you don't have too much experience with building complex projects, I would just capacitor couple it and just not worry about the DC element, because it can certainly get a little bit more complicated, a little bit more involved when you're designing the servo circuit. So that's the reason why I left out the servo. Okay, so that is what we have for the general schematic here, the topology. And we do have to pick op-amps, and we could probably talk about op-amps for hours and hours and hours, but I just want to be really concise on what specs for op-amps you should be paying attention to. And the first one that jumps out, the first spec that jumps out for U4 is going to be noise. We are very, very, very concerned about noise, because how much gain follows this op-amp. Whatever noise is going to be at this node is going to be much larger at 1 kilohertz, 100 times larger on the output. And so what we want to do is we want to pick a low noise op-amp, but we also need to factor in a few other specifications. The next specification that I'd like to talk about is the input offset voltage. And we've already discussed that that's really important for not having too much DC. If you had some op-amp that, had a horrible DC specification, well, you're just going to get more offset right here. We have blocked this, but you would still get, at roughly 14 times more, offset on the output here than the input. And that's not very desirable. So we want to go to a op-amp that has a great DC specification, considering that it also has great noise performance. And so for these, for this stage where we're coming from an cartridge, if you look at the impedance going into the cartridge, which is simulated with L1 and R38, it is not very low. It is somewhat high. It's significant source impedance. And so for amplifiers that have to amplify a signal coming from higher source impedance, JFET amplifiers are actually preferable and have better performance when amplifying a signal coming from higher source impedances. And this is particularly because JFETs have a really low current noise spec to them. And so the current noise is actually what you're worried about when you're talking about an input. The reason being is that how do we measure current noise on an amplifier? Well, we would actually terminate the input to that amplifier with a high impedance and then measure the noise on the output when we're measuring voltage noise, which is what most people are used to. It is that you would short the input and then measure the output noise. So we want an amplifier that has a low current noise spec, as well as a low voltage. We also need to keep the voltage noise in within means as well. And so that's why we pick, on this, you could go with OPA 2134. It has a very low current noise specification. It has, low noise, low voltage noise. It's not ultra low voltage noise, but it's got, I think, like 8 nanovolts for the voltage back here. So that is generally what you need for the and exceeding that will lower your noise. Exceeding the specifications of the 2134 will lower the noise of the phono stage if other factors aren't dominating, like this R21 or R24 can dominate as well. So, but the OPA 2134 is more than enough. It's not going to be audible noise, and so it has been used in probably hundreds, if not thousands, of phono stage designs. So that is yeah. So that is one of the next specification, and we're getting a little bit more in the weeds here. It's going to be less important because most op-amps meet this specification, but open loop gain is something that is important to us. And the reason why it's important to us is because unlike a preamp or the input of a power amplifier, we're applying a lot of gain. This is 23 dB here and 17 dB here. That is a lot of feedback that is being removed, a lot of correction that is being removed from the signal path. So we want high open loop gain because we want to make sure that we still have adequate feedback, specifically at high frequency, where feedback in these amplifiers are, you have a lot less open loop gain at high frequency than you do at low frequency. So we just want that to be as high as possible so that we still have adequate correction at high frequency.
Okay. One quick question, because we all know that DIYers love to roll op-amps.
Yes.
And besides all the variants of OPAs and JRCs and muses and everything else, which is quite obvious, just match the parameters. How do you feel about using discrete op-amps in here, like the things that Sparkers does, or other companies, or Borson?
I think it's great. Yeah, and those designs would be stable in this topology. I mean, we haven't done anything odd, and we haven't loaded it with any weird capacitive loading. I do have R27, if you notice, is separate from R24. We haven't discussed that. That's simply that you need to terminate these op amps very close to their output on this is more of a layout thing where I always put a small resistor right at the terminal of the op amp output. What that does is it isolates the trace capacitance, which is this line right here. And then I get to move R24 close to the input of U1, and that reduces the capacitance that's seen here. And so you reduce the parasitic RC because we're coming from a higher source impedance now. So we need to be careful that we don't create, some sort of crazy parasitic capacitance. Probably from 2.1K, it wouldn't matter too much, but it's still a design philosophy that I always do is I make sure to optimize that layout where we would want this to be small, we would want this to be really short, and this is the trace that we would actually route out to connect the two stages. And so
speaking about what about other nodes? I think especially the inverting nodes are pretty critical.
Yeah, so this so right here in your virtual ground node, let's make this really short. So these capacitors running fairly close to the inverting input on U4. Some people put a little isolation resistor to isolate the feedback coming back because this trace will be longer, and so you do have to worry about how long this trace is as well. But you're better off reducing the length of your virtual ground trace, and then just optimizing this. If it's for some reason, if this is very long, like in a power amplifier, you have to, bring it back quite a ways.
Yeah.
You could put in a little isolation, like 10 ohmer or something like that, right where you bring the feedback back, and that can isolate that trace capacitance, and that can cause, or that can reduce the chance of oscillation and creating a condition of instability in the amplifier. So because we've done all those things, I think that the discrete op amps would be fine. They do vary a lot in all these characteristics. Like Sparkos is going to have higher amounts of open loop gain versus some of the really old, the older designs, the older pro audio designs have very low open loop gain.
Yeah.
There's something about the discrete op amps. We're getting thick in it, so I'm going to be concise here as well. But they're going to have a more consistent open loop bandwidth. So their open loop gain versus frequency is going to be more. It's going to be flatter, and so that means that you're going to have higher. Not only are you going to have higher feedback at high frequency, which is very advantageous and desirable, but you're going to have a flatter amount of correction applied versus frequency. And that right there, that is why they sound better. It is. They do sound better, and it's because of this constant feedback versus frequency that is applied. Okay? This is a very deep topic. John Curl is very much so. This is one of his major focuses. All of his equipment has these characteristics of trying to keep the feedback that is applied at 20 kilohertz the same as the feedback that is applied at 20 hertz. And it's a very, on paper, it doesn't seem it's very important, but when you notice the differences between a high performance discrete op amp like a Sparkos and in a monolithic design, one of the largest contributors to that difference in sound is this phenomena that we're talking about.
Yeah, and Sparkos has a really good white paper about this too, so I will link it down below so people can see it, because it's really good.
Yep.
He's also a sweet guy. He's the best. Like, he's so nice. Sparkos.
Yeah. That's great. I don't know him. No.
Oh, no, he's great. He's a fantastic.
Awesome.
He helped me a lot.
Great.
Yeah.
Great.
Shout out to Thomas.
So, so there are many. This is a super deep topic. I'm gonna just breeze against it here, which is that in monolithic designs, you cannot create large capacitors on the monolithic die, and so that stops you from being able to implement higher order compensation methods internally. And that is one of the reasons why they have to have such an aggressive compensation roll-off. But not only that, but a 6 dB per an octave roll-off on the compensation because they're trying to create an op-amp that is going to be stable, even in unity gain, which is going to be one of the hardest points to stabilize the amplifier in. So they're really not able to, because of these higher order compensations needing larger capacitor values. They're not able to do that on the die, and they also really don't want to burden the designer with having to stabilize it themselves. They just want a chip that's just going to work no matter what and not cause a bunch of fuss. And so that's one of the reasons why that phenomenon exists. There are other reasons, but that is one of the main reasons why our monolithics don't always have great open loop gain at high frequency. Okay, so let's zoom out here. Hybrid RIAA, we've described how that operates, how that works. Our output here, if we go, we could create a formula and say V out divided by V in, which is the definition of our gain transfer function. And if we look at the gain and the output, and I adjust that, oh, see, we still have our rumble filter on her. Why are we getting such a... Okay, I don't know. But if you look at, we're relatively flat within this range. I have done something. Oh, I have not. You know what it is? I have not done.
Haven't rerun it.
I haven't rerun that's still with the rumble filter. Yeah. Okay. So now if we adjust, yeah. So okay, yeah, and this is another issue. I just want to show what it looks like without that. Rerun that. Okay. There we go. All right. So relatively flat response, plus or minus 0.2 dB, if you will. You can always tweak to get further in. If you want, or if you have just remember that your design when you build it is going to likely differ a little bit because we're being so picky on a very small tolerance here. So we'll get too obsessed with spending a whole day trying to dial in just the right values, because then you build it and it's gonna be different. So you want to just get it in the ballpark. If you do have a way of measuring the frequency response and building an inverse RIAA, you can, and then dial it in on your bench. But I just wanted to show you the end result here. We have V out divided by V in, our transfer function, going back, adjust it, and we have, okay, because I have this saved, it won't save for, I see. Okay, well, anyways, you can see the response is flat across the region. And when we do look at the transfer function, we do have roughly our 40 dB. So that's that. I'm now going to just quickly go over different ways of implementing the filter. And so we already see that this stage is the same. But what we're going to do now is I'm going to show you what's called passive RIAA. It is the oldest form of correcting this curve and applying the EQ. We've pretty much taken this stage, we've adjusted it for a little bit lower amount of gain in this stage. So I decreased R6 here. And now this right here is our entire EQ section that has all three time constants in here. And so if we look after this, it's relatively flat right after this passive network. So all of the time constants are in this, and then we follow it with a stage that just has wide bandwidth gain, and we have to apply a lot more. If you notice, 47K divided by 530 plus 1, this is a lot of gain. This is roughly 40 dB of gain now. And so why are we doing that? Why do we have so much gain? And the reason is that with the passive network, we actually lose 20 dB of gain right here. And the reason is that if you think about it passively, what are you doing here? Is that we are bringing everything down to this lowest value. So the two curves to look at are, this is the phase, that's the phase, this is the amplitude, and that is the amplitude here. The output is this flat, and then the input is this inverse RIAA curve here. And what we see is that we're knocking all this down. And so we're actually losing 20 dB because we have to boost all the way up, where before we just had to boost this side from 1 kilohertz all the way up to our output amplitude. Here we have to take it from here all the way up. So we're 20 dB, we lose 20 dB of gain doing that. So you have to put 20 dB more into your output stage. So right away you can start thinking of some problems with this. One problem is that noise is going to be a problem. Look at the value now, the series value. This is a much higher source impedance. You have a higher, your output stage, although it shouldn't dominate in noise. If it's amplifier that doesn't have a very good noise, a voltage noise specification, it very well could dominate noise or cause issues here. There's another problem, which is that the amount that we're going to have to drive at this point, because it's being attenuated, the gain is actually now before, and your overload is also going to be lower. So you don't have as much headroom with passive designs versus having it in an active implementation. So these are like the downsides. The upside to this design is that feedback burst frequency is not affected at all. So if our amplifiers are, let's say, like really nice Sparkos amplifiers, we're not actively changing the feedback that is applied versus frequency. You're actually getting flat feedback versus frequency. Here we're actually changing the amount of feedback. That's how this works, is you're changing how much feedback is applied versus frequency. And like we said, sometimes that can be advantageous when or it can be advantageous to have a flat correction curve. And so the passive designs actually do that. So that would be seen as, I think that's more of a subjective reason than an objective reason. But there are subjective reasons why passive might sound better, and that's one of them. So so I think that's pretty straightforward. I mean, you can go online and find passive EQ calculators too.
Yeah.
I just kind of dialed these values in prepping this, but it's something that you can find online, and if you want to create a passive design, that is how you would do it. Okay. Do you have any questions on the passive design?
No, I don't think so. It all makes perfect sense. And you mentioned like some people subjectively preferring that. And one of the most popular phono preamps for DIYers on DIYaudio.com is a Le Pacific, which is a passive preamp with 2 JFET stages, which is basically the values on your simulation are probably in the ballpark of that project because of like there's not much you can do.
No, you want to go with capacitors that you can find, and also with this, you are going to want to use high tolerance capacitors. So the amount of capacitors that you can use or what's available on the market, there is limited, and so you do want to stick to those big values here. You can see 100 nano, 33 nano, 1 nano that I use. And then the resistor values, you can always series resistors. You always make whatever you need out of splitting the resistance up and just putting stuff either in parallel or series or a combination of parallel and series to get these odd values. But you're better off doing that than you are finding high tolerant odd capacitor values. I don't recommend it. I recommend sticking to these big standardized values.
Yeah, and if you can't find high tolerance capacitors, just use smaller values in parallel, because their error will cancel out.
Right. Yep. Exactly. So, something to look into if you want a high performance capacitor that's not going to break the bank. I do recommend the RIAA FKP series. You can find that in Mauser DigiKey. And you can get 1%, 2%, and 2% values in that series. So, okay, so that's our passive. What was that?
This episode is not sponsored by RIAA.
No, it's not. It is not sponsored by RIAA. So, moving on, I have a third option, which is something that many may not have seen. It's something that's not really discussed much. You can find some information on it, but very little. And I don't really know how much this has been actively discussed. But I'm going to discuss it right now. And this is called split pole passive RIAA. And so what we're doing with this design is, again, I will say, just because we've added a stage here, this is your input. Your cartridge is right here. So yes, we have 3 stages before we had 2 stages in our design. So the first step is that we want to buffer the input signal from the cartridge. And the idea is to drive this early network very similar to our 75 microsecond our time constant that we applied on the input of this. We're going to be applying it much earlier so that it's actually, there has been no gain applied to the system, but we're applying that time constant, and you can see right there, we shelf it down and we've applied our 75 microsecond time constant before we've applied any gain. Again, the important element to this is that R19 is low in value. At 75 or at 750 ohms, it still may be dominant in the noise just a tad bit. It's acceptable, but this is still right on the edge. And I use that because we want to stick to a standardized value on our cap, and we also don't want to get too high on the capacitor. And then R19 is being driven at high frequency by U10. So we do have to, we we don't want to use 75 ohms. So 750 seems like a logical kind of compromise. You could go down in value a little bit. You could cut that in half and then double C32 if you want. That would improve the noise performance, but make sure your U10 can drive that impedance at high frequency.
Yeah, exactly.
So
every op-amp can drive 300 ohms. We have to remember that. Most of them are good to driving 600 ohms. The old standard. But not any capacitor can, not any op-amp can do 300, so you would have to check beforehand.
Exactly. So this is why I picked 750 for this example. I've applied the 75 microsecond time constant, and then what we're going to do is we're going to apply our gain now. So I've applied a gain of 11 here. So R30 divided by R29 plus 1. And we end up with this, which is now that 11, factor of 11 applied to it. And then we're going to have our 318 microsecond pole and our 3,180 microsecond pole, our I apologize, I misspoke. The 500 0 and the 50 hertz pole, and so our two time constants at 318 microseconds and at 3,180 microseconds is applied right here. Okay, and so picking these values, it applies to just like the passive. We want a compromise in being able to drive this, but we don't want it to be too high for noise reasons. Our output stage is going to be very similar. It's exactly the same as our passive design. This one applies, a little bit over 40 dB of gain across the frequency band, and on the output we get our flat response here. So that one works as well. But what we've done, why have we done this? Why have we applied the time constant so early? And the advantage here is just that we knock the top down earlier. So we bring in some of the advantages of that hybrid design, which was number one, with the passive design, which was the second design we talked about. And we kind of get best of both worlds, other than having to add in another stage and having R19 be on the line of dominating noise in this design. So that is, so it's another compromise, but some might argue that it's a better compromise than the ones above this, just because you get the advantages of having to run these amplifiers, with a constant correction versus frequency, but at the same time having some of the overload advantages of introducing that 75 microsecond time constant earlier.
Yeah, what comes to my mind looking at this, if we are concerned about the noise of the first stereo buffer and the R19, I had to do like manual zoom, with my head. But if we are concerned with that, we can always just use two buffers in parallel and lower the impedance of R19 and up the R32.
Yeah. So another thing you could do too is, hold on. Yeah. Are you saying to parallel the buffer right here?
Yeah. This is two.
Well, so the noise is actually being dominated by R19.
Yeah.
The noise is because we're putting gain after this series impedance here. Mm-hmm. And so adding two buffers in parallel it would only reduce the voltage noise of this of what is being created, or I should say the noise overall that's being created on the input of this amplifier. You would lower that by 3 dB, but you would not fix R19. But what you're saying is that you would have better drive capabilities, so that then you would be able to lower the R19. So that's one idea. The other idea is that you could put in, let's say, only 6 dB of gain here, right? So you can shift gain over. So you could say, well, I'm just going to put in, what's 6 dB in a non-inverting amplifier? It's, we could put, we could make a non-inverting amplifier like this.
Yeah.
And what's 6 dB? Well, we could just make, let's say that we're going to have to make this, so you can kind of see we're going to run into a problem here.
Yes, I can see that coming.
See the problem coming, yes, which is the reason why now looking at it, this is why I don't design, when I use this design, why I don't use it. But you see, this is going to give us 6 dB, but you see now that the amplifier has to drive R38. And so, that's problematic from a perspective of just loading this down too much. So for that reason, I'm actually much more of a fan of your idea of paralleling the buffers, which you can do. What you might be able to do is you might be able to actually build a little bit of their isolation into how you isolate or you might be able to build in their isolation resistance into R19. So let's just design that really quickly. I'm gonna put isolating. Isolating resistors. See, this is actually all this is not. I'm not dragging this right. So 1 second. So let's isolate these stages, because usually what you want to isolate when you put amplifiers like this in parallel. You're going to want to isolate it. So we could we're kind of designing stuff on the fly here, but we could do that, and we could actually just tweak these values to make what we want. So we could say 1.5K, 1.5K, and we would end up with our 75 ohms of source, and we would be able to isolate those two impedances, or those two amplifiers, which is generally a good idea when you're talking about paralleling, and then we can just do that, right? So that kind of solves a little bit of your issue. Now you can see that now we have room to move these down. So now we could just, let's
let's just make it. Let's make each one 750. And then bump the 32.
750.
Yeah.
And then 200. And that's easy, because you could just parallel two 100 nanos. Yeah. And boom, so now you have something. So that's a good solution to getting the best of both worlds. But I'll say this has not been talked about too much. It's something that I stumbled across the idea in my head, and then realized that other people are doing it. So I never came up with it, but it's something that I will say I'm a huge fan of this one. Sometimes in this, this discretely is kind of a big deal, adding another parallel amplifier, discretely is sometimes, not the most advantageous depending on the type of amplifier. But with your ICs, you can just use, the other channel to the 2134 and then just have one 2134 per channel. And so that's a good compromise to be able to, drive this impedance and keeping it low and dealing with that noise. Just remember that your buffer, it also does need to be, relatively low noise. You don't want to use something that's like 20 nanovolts or something here. You want to keep it low. But if you use 2134 and paralleling this now cuts it down 3 dB. So this is an interesting design. For those watching, I will say that this is very intriguing to build. Given these op-amps, I would say that this is actually, at the very beginning of all this, I said I recommended the hybrid. I've actually changed my mind. I think the pole would be a cool design to do. Yeah. Okay. Well, do you have any questions?
The last thing that I think is very, very important is the question of power supply. So I know we are running out of time, and we are actually...
We are.
But if we can touch quickly on the power supply, I think that's gonna be it.
Yes. So power supplies and phono stages are obviously going to be incredibly important. We have so much gain that we're applying to the signal that the noise on our power supply is very important. Now, if you're using these monolithic op amps, a lot of these designs have excellent PSRR, and so their power supply rejection ratios are very high. So they're going to reject a lot of the noise that is on the power supply, especially in the audio band. And so that is working for us. And so, some people use batteries in these designs. Some use, very traditional linear power supplies, like using a Allen 317 and 337, to create your rail voltages. That could be a good option that is simple to design into this. That is almost like, taking a solution off of the data sheets and making a linear power supply with it. And then we get to the more advanced side where we want even lower noise than that. And the next step would be to use higher spec, integrated regulators. You can get, from, linear technology, for instance. There's a lot of excellent high bandwidth regulators that will perform better. And what do I mean by high bandwidth? Because when you think about regulators, you think about, DC. So how's their bandwidth? And the answer to that is it's an attenuation bandwidth, a rejection bandwidth of if we were to insert noise across a frequency band into the input of that regulator, how much does the regulator reject and attenuate on its output? And so an Allen 317 really doesn't have much bandwidth at all to it. 100 kilohertz maybe. But there are more advanced, higher performance regulators on the market that can run, a megahertz plus of decent. I'm not talking about a 3 dB bandwidth spec, but just having decent rejection up to a megahertz. You can find those. And so I do recommend dabbling for those people who feel comfortable with that. You are going to have to do surface mount probably for those more advanced ICs, but that could be a really interesting design. Is using those advanced regulators for phono stages would be, I think, very advantageous. And then the next step above that is discrete regulators, where you get to use, advanced error amplifiers by using really nice, opamps, like integrated opamps that have high slew rates, and that can offer a very wide bandwidth of correction. But obviously, it's more advanced at that point.
Yeah, it is. There's this really, really cool dual positive and negative regulator from linear technologies, but I can't remember the name. But I will just post it on the video. People can see it, but it is in QFN. So it's a pain in the ass to solder, but it is a very promising part.
Yeah, there are great parts out there, so you can use that. That's I wish we could go a bit further in. Maybe we could do a power supply video in the future, but
I think we should.
I think this will give people a lot of places to start, and I mean, we were just designing on this, so feel free to modify these designs and try something and come up with your own compromise, which is the art of engineering.
Yeah, all these simulation files will be available on our GitHub, so you can download it and just play along as we are talking on. Just as Darren said, just choose your own adventure. I would like to thank you so much for coming. It's been incredible. I learned so much. You cleared some things for me, so thank you for that. And maybe I'll do a PCB for the last design so people can try it.
Yeah, absolutely. And thanks for having me, Mikhail. I really enjoyed it as well.
Yeah. See you soon, hopefully.
Yeah.
And thank you.
All right. Okay. Thank you.